It's better? Is this lighting better than before? Yes? Thanks. Okay, so let's start. I want to start first by reminding us where we were last week. We are still introducing ourselves to machine learning, and basically this figure is one of the figures that kind of summarizes the protocol or the methodology that we talked about, along with some notation. So the problem that we have is there is some input. We call this the instance space, capital X. There's instances in it, or items X. And there are labels, Y. And we are seeking a model, G of X, that maps X to Y's. Basically, that's our goal, to find this function. And we want to find a function that matches some kind of a target function that maps X to Y's. So we talked about this, we introduced some notations, and then we played with this toy problem, this learning example where we had 4 variables. We asked what the hidden function is, given that I gave you these 7 examples. You had some good guesses, and then when we discussed it, we realized that actually the problem is very, very ill-defined, because there are many functions that could be consistent with these 7 examples. And you have no way to choose one over the other among all these. So this led us to discussing the question of whether learning is possible and introducing the notion of hypothesis space, which is very important. Basically, the set of functions that we consider as candidates for a learning problem. And while this hypothesis space sometimes is not explicit to you, when you just use packages, it's always there. You always make choices. And some of these choices are explicit, and some of them are implicit in the way the algorithm learns. It cannot learn everything. It is biased toward specific spaces. Okay, so this was just a reminder of what we've done. And then we said, okay, that we're going to deal with 2 issues, and this is where I want to continue today. The issue of modeling, how to formulate application problems as machine learning problems, and what kind of learning protocols are we going to use when we do it. The issue of representation, tightly coupled with modeling. What functions are we going to learn, and how are we going to represent the input? And the issue of algorithms. What algorithms are we going to use to map input to a label space? So that's what we're going to, we kind of hinted on that last time. That's where we're going to start today. Before that, I want to talk a little bit about a few administrative issues. So first, the class is full, even though there are some spaces here, which is unfortunate. So all people that were on the waiting list, category less than 5, got in. If you think otherwise, let me know quickly. Some of the people, I would say most of the people that were in category 5, or at least half, also got in, not everyone. But we will support petitions of people that want to get in. So if you're still on the waiting list and you didn't get in, you can still get in, because my assumption is, it's not an assumption, it's completely clear that some people will drop the class, and therefore there are going to be additional slots. So we're also considering moving to a larger classroom. We'll see what happens. Just because we stopped shy of admitting everyone, because this class is on paper completely full. Who is here on the waiting list? 1, 2, that's it. 2. And you have not received permits yet. Okay. On the real waiting list, there's a lot more than 2. So I don't know if that means that others just caved in, or they're counting on the videos, or they just know everything. But we'll see. We'll see what happens. But it's pretty clear to me that you'll be able to get in if you're willing to petition. Okay. Homework 0. Everyone needs to do homework 0. I'm not going to ask, but this is mandatory, which means you're going to lose points if you're not submitting it. Everyone who wants to be in this class has to submit homework 0. If you haven't done that, please do it quickly, and in your email, say something about why you didn't do it earlier. We're going to accept it, but you have to do it quickly. Hopefully, all of you did quiz 0 that we made available over the weekend. The idea there was basically to give you a chance to be more prepared Python-wise. I know that about half of you are fluent in Python. I know that about half of you are not. So you'll have to work on it, and the more you work now, the more efficient you're going to be when you have to do the problem set. So please take this seriously. We have today a second recitation on Python. Questions on that? Yeah?
Is that recitation going to be similar to the lecture?
It's going to be more hands-on. So the idea is that a few of the TAs are going to be there, and they're going to help you set up and answer questions. Other questions on that? Okay. Starting this week, there's going to be quizzes almost every week. The idea of the quizzes is that basically we want to make sure that you follow what's happening, and you come to the Monday morning lecture with, the information that we covered earlier, kind of at the top of your head. It's going to be made available Thursday midnight or before. It's due Sunday midnight. So you have a few days. It's supposed to take 5 to 10 minutes. Hopefully it won't take more than that. This is actually part of the grading of the class. Questions? Yeah.
Do we have several attempts?
Yeah, I think every question gives you 2 attempts, something like that. I will not be able to stay today after class to answer questions because I have to catch a train. So all the questions, anyhow, the questions are of interest to everyone. Please ask them now. Registrations, homework, quizzes, yes?
Are you planning on posting a write-up of the solutions to homework 0?
Yes, yeah, there will be a solution. I'm just waiting because I know that some of you haven't done it yet. Okay, and as I said in the Piazza note, I don't have office hours this week. The TAs do, so please use it if you need it. Okay, so let's move on. So I showed this slide before. That's what we're talking about now. And let's start with an example. So here is a machine learning example, or I want to make it a machine learning example. I don't know whether to laugh or cry. And you can spell this 2 ways. The red weather, the blue weather, and I assume that you know the answer. You can try it on your word processor or Google Doc or whatever you want. They don't know it. So we want to write a machine learning algorithm that figures it out. That determines which whether you want to put in the context of this sentence. Which one should we put? Which the right one? Yeah. The red one is the right one. Okay. So how do we make this a learning problem? Right? So of course we don't want just to make this whether a learning problem. We want to be able to make it a more general, context-sensitive spelling correction program, but we're going to focus now on this specific whether problem. So what should we do? So the first question for us is, what is the game we're playing here, right? So we're looking for a function that takes a sentence, let's say with a hole in the sentence, or with a word we're not so sure about, and maps it to one of these two options, blue weather, red weather. Right? So that's what we're after. Now, just saying F maps sentences to weather is meaningless. I really need to define the domain of the function in a concrete way so that I can do something, right? Suggestions. What would the domain of the function be? Domain here is a technical word, right? The domain of a function. What are the options that you can think of? Something. Yeah.
Dictionary size cross 100 sort of space. So
What do you mean?
So basically a real space whose dimension is basically dictionary size cross 100, where I'm limiting the sentences to be less than equal to 100.
Okay, so basically what you're saying, let's assume that all my sentences have length up to 100, and all I know about the sentence is the words that appear in it. So I'm going to take a space that is the number of words in my dictionary, let's say 50,000, times the length of the sentence, so that I will be able to say which word is there, and this will be my domain. When you say that this is your domain, you also have some idea of how to encode the sentence, right? So I said F maps sentences to something. Really, we need to figure out, so how do we represent a sentence? So any suggestion of how do I represent a sentence here? Yeah?
Encode the words in it to some, like if the assign a specific number to every sentence, every word, and then make it a vector.
Okay, so basically every word is going to be a number between 1 to 50,000, and then
we replace the words with the numbers and make that into a representation of the sentence.
okay. That's a good idea. What is the limitation of this? If I have a sentence of size 10 versus if I have a sentence of size 20, what will happen to this representation?
We have to add the sentence of 10 to make it a constant.
Because otherwise it will be variable size representation, which we may be able to deal with. We're going to talk about it, but remember that this could be an issue. We often like to have same size representation in the input all the time. Okay, so these are good suggestions. Any other suggestion? Yeah.
You might want to get the stems of all words,
The stems of all words. Why?
because that's the actual word, and the stem, it reduces the number of words we have to look at.
Okay, so that's a very interesting suggestion. So you want to distinguish between a sentence, I don't know whether to laugh or cry, and I didn't know whether to laugh or cry, right? So maybe it's a different sentence, and I want to encode these two sentences in the same way, right? So whether it's don't or didn't, who cares? From the perspective of solving this problem. So the suggestion here is to do some abstraction over the words in the sentence. And that's actually an excellent suggestion. We're not going to do it now, but it's an excellent suggestion, and we'll see later on. So here is an option. I'm going to simplify the suggestions that you've given me so far, and but it's going to be quite similar. So my representation for now, this is just one option. We're going to see others. For each word in the sentence, I'm going to define a Boolean variable, picture. It's going to be called XW for the word W. And it's going to take the value 1 if the word is in the sentence. Otherwise, it's going to be 0. That's it. Now, my sentence is going to be a point in the 50,000 dimensional space. 50,000 is the size of my dictionary, where most of the 50,000 dimensions are going to take the value 0. And a few of them, those that are present in the sentence, are going to be 1. Okay? So it's going to be a very, very sparse vector of dimension 50,000. Everyone agrees that's a representation of the sentence? What did I miss? Yes?
You could probably drop some words with small numbers of occurrences because their likelihood of being in a lot of sentences.
Okay, but they are there in my dictionary. So what you're saying, you can use a smaller dictionary. I could do this, but already with this representation, I lost something. What did I lose? The order. I didn't represent the order, right? It's basically a bag of words, what we call. I lost even what's before and what's after my target words, whether. I just know what's in the sentence. Okay? So maybe it's not the best representation, but it is a representation. We could make it, if I want to encode the position, my dimensionality is going to go up, right? Because for each word, I'm going to have to encode whether it's in the first position, second position, third position. Maybe as you suggest, let's assume that the length of a sentence is up to 100. So up to 100 positions, that's going to increase the dimensionality quite a bit. So let's not do it for now. But that's a representation. So now I have a vector space of dimensionality 50,000. In this vector space, I'm going to place weather sentences, blue weather sentences, and red weather sentences. So each sentence is going to be a point in this space. So what we've done so far is the modeling, right? So we thought about how do we make this. We also talked about the input space, the instance space. And now I want to ask you, now that we have an encoding, I want to make it a learning problem. How do I learn? Right, so I have a high dimensional space. I have blue points and red points. Yes?
You could maybe define a boundary. Anything to one side of the boundary would be red weather. Anything on the other side would be blue weather.
Okay, but even before that, we're going to do something like this is, what is going to be my learning protocol, right? So what do I need in order to make it a real learning problem? So far, we are in the abstract. I have one sentence, and we talked about how to encode it. But really, in order to make it a learning problem, what do I need? Yeah? I need data. I need training data. So where do I get my training data? Yeah? Sentences that are correct. So I can ask each one of you to annotate some sentences for me, or any other suggestions? Yeah?
Call Wikipedia.
Under what assumption?
Wikipedia is correct.
Okay, so I can go to Wikipedia, I can go to the New York Times, crawl sentences, assume that someone edited it, and for the most part it's correct, which is true for the most part. They have some typos, and they have some context-sensitive spelling mistakes, but 99% of the sentences are going to be okay. I'm going to take only sentences that have either weather, blue weather or red weather, and this is going to be my training data because it's already labeled under the assumption, labeled correctly, under the assumption that someone edited it and verified it, right? Now I have training set. I can also generate from this a test set. Right? I'm going to take 20% of this data. I'm not going to tell my program whether it was a blue point or a red point, and I'm going to use this 20% to test my model after I learned. Okay? So we have a methodology. Now, is this a supervised learning problem or an unsupervised learning? Someone there that answered. Just raise your hand so I'll see who you are. Yes.
Supervised,
Why is it supervised?
because you're telling the program which ones are red, weather, and which ones are blue.
Right, so my learning algorithm is definitely a supervised learning algorithm. However, there's something interesting here. I didn't have to work, not hard at least, to get the supervision, right? I only made an assumption, right? The Wikipedia assumption, the New York Times assumption, the assumption that somewhere in nature there is good data for this problem. I had to think a little bit about how to get this data. In this case, it was very, very easy. But I did not have to label the data, and the data that I got was not labeled specifically for my learning task. It was out there because people want to write articles in Wikipedia and in other newspapers, right? So it's supervised in terms of the algorithm, but it's not supervised in the sense that no one had to annotate this. And this is actually an important distinction that in today's machine learning is really important because people realize that it's impossible and sometimes makes no sense to actually try to annotate data for each type specifically. So there's a good question of how can we go out there and find data that has been there anyhow and use it to learn from. And this is what we've done here. Okay, what is our hypothesis space? In fact, we haven't said, right? I just said F, map sentences to weather, and now we want to be a little bit more specific. So here is our learning problem. So we took all the sentences that we found in Wikipedia, we placed them in our 50,000 dimensional space, which is here. Looks like 2, but it's 50,000. Some of them are blue, turn to purple points, and some are red points. And what we want is we want to find a function that separates this data. So what kind of function can we do? Here is a function that perfectly separates the data. Here's another function that doesn't separate it perfectly. And here are a couple others. So which of these should we choose? Any idea which of these you would choose? Yes?
Depends on how it's doing for your testing error. Or your, you have like a medium. You want to minimize, you want to train the model on one, and you want maybe a small amount of it that you get preliminary.
True. So basically what you're saying, really, I don't care about how it's doing on the training. I care about how it's going to do eventually on the test. What do you think here? Which of these functions is going to be best on the test data? Yeah?
I assume the blue line is going to be better than the green squirrel,
Right. Why?
because the green squirrel is probably overfitting.
Right. Excellent. So we're not, without defining anything, the intuition is that you can always draw this green squiggle. I mean, give me data. If the data is separable somehow, you can draw it on the training data. But every slight movement of a point, purple to the right, red to the left, or vice versa, is going to cross to the other side. On the other hand, the blue one, say, doesn't separate it perfectly, but seems like more stable, simpler, right? Going back to the first class when we talked about simpler. And in fact, that's going to be right. We'll have to define best. What do we mean when we say best? So one suggestion already is define best not based on the training data, but rather based on the test data. That's what we care about. But we don't have the test data, so how can we do it? We'll have to think a little bit about it. And also, best has many definitions. Best in terms of mistakes, or best in other senses. So the issue we're talking about it is really memorizing, which is what the green thing is doing, versus really learning, or accuracy on the training data versus simplicity. And as I said, so this is an important issue. We're going to come back to it in a more rigorous way. How well will you do in the future is important, and all these really have impact on generalization. We said at the beginning, what we care about is generalization. Of course, we're going to care also about how to find this, and for now, my suggestion is going to be to define the learning problem in a somewhat narrower way, rather than just find a function. I'm going to suggest, let's find a linear function. So I'm already restricting my hypothesis space to be the set of linear functions that best separates the data. What do I mean when I say linear? Now we are beginning to introduce some notation. You're all fluent in this because you've done the linear algebra problems in homework 0. So everything is fresh. Linear, by linear, I mean linear in the feature space. X is my data representation, my instance. It's a vector. I'm going to think about these vectors. Everything that is bold, modulo typos that I've made, is a vector. And I think about vectors as column vectors. So X is going to be my data representation, this 50,000 dimensional space we talked about earlier. W is going to be my model. And it's linear because I'm assuming that the function is basically the dot product between W and X. So my Y is this sign of dot product between W and X. This is the dot product, right? And when I say sign, I mean if the value inside the parentheses is negative, say 0, negative example. If the element inside the parentheses is positive or 0, say positive. Okay? So basically, Y is going to be computing the dot product between W and X, and it's going to say positive if this dot product is positive. Otherwise, it's going to say it's a negative example. That's going to be my model, which is basically the blue and the red and the brown lines here. That's what they're doing, right? So these are linear functions in the space, yes?
You also need to add a bias term, right?
Yeah, we'll get there, yeah. So we'll add a bias term because the way I've written it now, it looks like all these linear separators are going through the origin. We're going to move it away from the origin in a few slides. But that's what I mean by a linear function. So now, first of all, this is the most general form. Yes?
When you just purify that, W would be like right into the line or the slope of the line?
We are?
You need to say like W would be the slope.
W is the slope of the line, yeah. Is the line, right? So, in fact, W is the perpendicular to what you see here. Okay, so first of all, I want to talk about expressivity. So the full form of what I've said before really has also a theta, which is a bias term that moves the line away from the origin. If I only have Wx, these lines go through the point 0, 0, and I don't necessarily want it to go through there. So now, is it a disaster that I'm only learning linear functions? So first of all, I want to argue it's not. Actually, many, many functions are linear. Linear functions are quite expressive. Example, conjunction. So this is a conjunction, right? It basically says if you want weather, then weather type 1, what was it? The blue one or the red one? If I want the red weather, I must have two following the target word. and I must have a verb after it. That could be, that's a conjunction. I have to have two conditions. Here I have a conjunction of three things. So that's a natural function in many cases, and I argue that this is a linear function. What does it mean that this is a linear function? What do I mean when I say that? Mathematically. I want someone. Yes?
There's a linear function that like have the same output if you have the same input.
There is a W that defines a linear function, a vector W, that behaves exactly like this conjunction. So how does this conjunction behave? If x1 and x3 and x5 are 1, y is 1. Otherwise, it's 0. So I want to find a W that behaves exactly, that makes the dot product, x dot product W, behave exactly this way. Suggestions? Let's assume I have just 5-dimensional vectors, so you need to give me W1, W2, W3, W4, W5. 1?
1 by 5 in all the W's.
What do you mean 1 by 5?
0.2.
0.2, I want something simpler. That's true. But even if it's 1 on 3 of them, so if W1 is 1, W2 is 0, W3 is 1, W4 is 0, W5 is 1. So the dot product becomes 1 times x1 plus, I'm not writing it here, 0 times x2 plus 1 times x3 plus, I'm not writing it here, 0 times x4 plus 1 times x5. Theta is 3. I argue that this function behaves like a conjunction of x1, x3, x5. Agree? So my W is 1, 0, 1, 0, 1. My theta is 3. I gave you a proof that this conjunction is a linear function, and you can do this for every conjunction that you want. Here's a more interesting function, at least m out of n. What does that mean? I have n. My dimensionality is n. I have n variables. If m out of them are 1, the function is 1. Right? Yes?
Just to clarify, your like little sigmoid-ish function that zeros if it's negative and 1 otherwise, is that unique to the case where you're working with Boolean variables?
No, it's not. It's a general function that says if something is, it's a sign function. SGN is a shortcut of sign, and it says if something is positive, the value is 1, otherwise it's 0. Was born much before sigmoid was born. Okay. At least m out of n. I'm going to take a specific example, at least 2 out of these 3. Is it a linear function?
I think you just replaced theta with n instead of n.
Okay, so basically use the same W that I had before and change the theta instead of 3 to be 2. Here is the function, and it's exactly this. So 1, 0, 1, 0, 1 is my W. Theta is 2. And you should be able to convince yourself that this behaves exactly like m out of n. So this is just anecdotal evidence, of course, but this is an expressive line, expressive set of functions. Makes sense to use linear functions. Now, of course, there's more, right? So all probabilistic classifiers we'll see can be written as linear functions. We're going to get to it in a month and a half or so. Some functions are not linear. So, of course, here is another function. It's called XOR. Many of you have seen it. What XOR means, I'm showing it here for the case of 2 variables, x1 and x2, or not x1 and not x2. You should have seen this notation, so that should be easy. Or any other function in disjunctive normal forms that are non-trivial. By non-trivial, I mean Of course, if x1 is equal to x2 is equal to x3, that function is a simple conjunction. But in general, when they are different, this is not. But the interesting thing is that functions that are not linear can be made linear. And that's a very powerful idea, and it's a very important idea for us to understand the importance of representation. Let's look at this example. So this is data. There are blue points and there are red points. And there's a function that separates them, right? Here's a function. This function separates the blue from the red points, right? But it's not a linear function. Can I separate these points, the blue from the red, using a linear function? Yes?
You would need to transform the data.
Right. What would I do?
X squared.
X squared. So that's what I'm going to do. So rather than representing just x, I'm going to represent x and x squared, which is magical because I did not add any information, right? I knew what is x squared before. If I represent the data this way, as x comma x squared, now I can separate it with a linear function. I moved from 1 dimension to 2 dimensions, but now there's a linear function in 2 dimensions that separates the data, which is magical and something that we're going to do a lot. Because basically, without adding information, just changing the representation, we are adding expressivity. So this is really an important thing. It basically asks, what features should I use to represent the function with? Not what information, what features. And these are different things. I did not add any information here. I just changed the representation. And we're going to talk a lot about this. Now, I can do this also in the discrete space, if some of you like discrete functions more than continuous functions. So my example here is, again, XOR function, x1 and x2, or not x1 and not x2. This is not a linear function in the 2-dimensional space, in the x1, x2 space. Can I make it a linear function? I'm going to show it in a more complex example. So let's assume the separation between whether type 1 and whether type 2 is complex. Maybe it's as complex as this function that I've written there. How to read this function? It's x1 and x2 and x4, or x2 and x4 and x5, or x1 and x3 and x7. A complex function, not a linear function in the space of the xi's. How do I make it a linear function? Transformation, just like we did in the continuous space. I'm going to invent variables. The variables that I'm going to invent this time are going to be, each variable is going to be a conjunction of 3 variables. So I'm going to have a conjunction for x1, x2, and x3. One for x1 and x2 and x4. One for x2 and x4 and x5, and so on. For every triple, I will have a new variable. In this space, once I define this y space here to be the set of all conjunctions, in the new space, this function is just a simple disjunction. It's maybe y3 or y4 or y7. Okay, so I basically did renaming. I increased the number of variables, but now the function is simpler, yes?
So you need to, on the outset, know what the function is in order to know what transformation to do?
I need to know how expressive the function is, not necessarily what it is. Because let's assume that you told me the target function has conjunctions of size 3. I don't know which ones. How many conjunctions of size 3 do I have on n variables? N cubed, right? So each conjunction is going to be of size 3, and I have n variables, so I can choose any 3 variables and make a conjunction of them. I have n choose 3 ways to choose. So the space of variables is large. Not all of them are in the function. I don't know which one are in the functions. I just know that some of them, 3 of them, 5 of them are there. So I'm going to invent n choose 3 y's, And I know that my target function is at this junction of some of these y's. I don't know which ones.
How do you know that?
If my assumption is that the function looks like this,
Right, I know, but like, how would you, let's say we take the weather example, like, how would
I have no idea. Excellent question. So here's the question here. So forget the technical thing that I'm doing here. I'm making an assumption here, right? So in fact, I made an assumption already here when I told you, you know, come on. When I said, oh, now it's moving. When I suggested, let's learn linear function, I made an assumption. You could have asked the same question. How do you know that it's okay? And in fact, I don't know that it's okay. And in my picture here, it's not okay, right? So the blue lines makes mistakes. It's not expressive enough. Nevertheless, I'm going to come up with some hypothesis space and hope that it's expressive enough to either represent my problem, the weather problem, or comes close to this. And that's it. There's nothing I can say beyond that, because I don't know what is the hidden function. I just need to assume that it belongs to some function class and hope that there is a member in this function class that either is completely consistent with the data, or in real life, pretty consistent with the data. That's it. I cannot say anything beyond that. So I'm full of assumptions here. And this is something you'll have to deal with. So I'm full of assumption when I say a possibility, define the learning problem to be, let's learn linear functions. And at the same price, I'm also making assumption here when I'm telling you, you know what, I'm taking the data and I'm re-representing it as x comma x squared. This may not be enough. It is enough here, just because I drew the problem this way. But it could have been something that x squared is insufficient, right? You can immediately think about it and draw blue and red points in such a way that x squared comma x will not be sufficient to separate it with a linear function. And in the same here. I just thought about the target function is a disjunction of conjunction of size 3, and therefore my y's that I invented are conjunction of size 3. Maybe it won't work. Maybe it will not be good enough. Maybe it will just approximate the function. But what is clear is that it will approximate the function better than just working in the original space, x1 up to xn, because it's a more expressive representation. So we always make assumptions here, yes?
So, I guess similarly, going to the point, about, sort of how deep they know about assumptions, maybe. In some sense, I can always imagine that in some high-dimensional space, there exists some manifold where data lives on, and I can do a plane that cuts through it, which then projects into basically any arbitrary shape on the lower dimensional space, which is what we're doing here, right? Is this just generally true? Are there data that you can explicitly say that you simply cannot find such a kind of representation?
Okay, so I think the model you have in your mind is correct. Let's take the Boolean case because it's easier to think about. Any Boolean data that is consistent, by consistent I mean that a given point has one label. I never see in my training data the same point as positive and some other time the same point as negative. If it's consistent, then there is a Boolean function that agrees with the data. This Boolean function can be very, very complex. Too complex for me to learn because the space of Boolean function is too large. If I have n variables, the space of Boolean function is 2 to the 2 to the n. double exponential. I'm not going to try to entertain all these functions. I have to make assumptions. And the assumptions basically are hypothesis space assumptions. I'm saying I'm going to represent functions that complex. And you can define the that based on many things. Your assumptions about the function space, your computational abilities, but you'll have to make these assumptions. Okay, so hopefully this gives you some idea why, two things. One, why is it okay for me to carry on for a large part of the class with linear functions? There are really three reasons. One is because they're quite expressive. Two is because I want you to think about representations. It's crucially important. Three, because all the ideas that we're going to develop for linear functions, not only the ideas, even the technical tools, hopefully we'll get to one of them even today, in fact are going to continue with us when we move out of linear functions, when we move to neural networks, for example. All of these ideas are going to be the same. Okay, so now I want to give you some real examples. So when we modeled the problem whether, we started by deciding that these blue and red points are going to be simple 50,000 dimensional spaces and just bag of words, right? So every sentence is going to be just essentially the list of words that are present in the sentence. In real life, that representation is not going to be sufficient. So if you click on this, which I will not do now because I have some slides that give some specific details, you will see real data that comes for this specific problem. And I'm going to give you a few slides on it. So this is what you're going to see if you click on this and look at the file. You will see that we have 4 feature types. What I'm saying now is actually important. I'm going to make a distinction between features and feature types. What are the feature types? So before you suggested to me one feature type. It was whether the word is in a sentence or not in the sentence, right? There was one other suggestion, which is whether the stem of the word is in the sentence or not in the sentence. That's not going to be sufficient. So I'm going to suggest a few other feature types. 1 and 2 together. So first of all, rather than the word itself, I'm going to encode also the part of speech tag of the word. What is part of speech? It's not written in the sentence. I'm assuming that I have a tool that looks at the sentence and knows whether a word in the context of this sentence is a noun or a verb or an adjective or a preposition and so on. That's the part of speech. So my feature types 1 and 2 are giving me the relative position of this word and the relative position of the part of speech of the word. I'm going to encode both. Feature type 1 is going to be the word relative position, and the feature type 2 is going to be the POS tag. And the way I'm going to encode it is relative to the target word. So I'm sitting on the whether in the sentence, and I'm looking at what happens to the left of it and what happens to the right of it. If it's plus, it's to the right of it. If it's minus, it's to the +1 plus or -1 is relative position to target. So for example, look at the first line there. It says 1p equal determiner. By that I encode that to the right of my target word, whether, there is a determiner. I don't know which determiner. It could be the word the, it could be the word a, it could be other things. The next one, the second row, can you read this? Says 1w is the word the. So it means to the right of the target word, there is a word THE. And the next one, the third word says, to the left of me, -1, the part of speech is a punctuation mark. I don't know which one. Could be a colon, could be a period, could be a comma, and so on. The fourth row, if we continue, it says that to the left of me, there is a part of speech verb, -1p verb. So these are features of type 1 and 2. Now notice that for feature types 1 and 2, I already listed several features, right? So the feature types are look to the left and to the right and tell me what's the word there or what's the part of speech there. Now this can be instantiated to make many, many features as a function of the words, the number of words that we see in our data, and as a function of the part of speech text that we see in our data. Feature type number 3 is a conjunction of size 2 of two things. So for example, we have to go down a little bit. Let's see, can you see? You cannot see the mouse, so which line is the first conjunction that we see here? Okay, let's go to the bottom row. Okay? The bottom row says 1p is ns, and 2w is the word word. So that's a conjunction of two things. It says 2 to the right of me, there is a word, the word is word, and 1 to the right of me, there is a part of speech, which is a noun. In fact, it's a plural noun. Okay, that's a conjunction of two things of type 1 and 2. And of course, you can see that there could be many, many features that instantiate this type as a function of how many words and how many part of speech. And feature type number 4 is just the word. This is what we started with. Just whether the word is present, but in fact, I don't care about whether the word is in the sentence. I only open a window of ±2 around my target word, and I only encode words that are there, under the assumption that too far to the left or the right, it doesn't matter. It's sufficient to look at local context. And again, you can see, if you look at the fifth row, you see or. OR appears in the sentence in a small window, right? I don't encode the position for this. I just encoded the fact the word is there. So these are the features that actually I'm going to encode for this problem, right? So now you can also do a little bit of counting, and you will see how many features you may have for this, right? It's going to be a function of the vocabulary that I see in my training set, right? Immediately as a function of the vocabulary, it's the part of speech. I'm going to see all part of speech somewhere. And I limited the size of the number of features by only looking in a small window, ±2 around the world. So these are all my features. So now notice I'm giving some examples. And I want to make sure that we understand that the features result from instantiating the type in the data. I gave you the types even before I looked at the data. These are the 4 types I think will be important. Just like at the beginning, you told me, we think that just encoding whether the word is there or not is sufficient, or encoding the stem is sufficient. Now I'm telling you, actually, I need these 4 types. So that's one. And notice that in addition to features, I also encoded some numbers. The 3 numbers to the right of each row are unimportant to the learning problem. They're just some statistics that I encoded. So basically, the last 2 numbers encode how many times I've seen these features with the blue weather and how many times I've seen this feature with the red weather. You see that in all the features that I show you here, this is quite extreme. It's mostly 0 and something, or something and 0, with a few exceptions. And I also encoded some statistics of the data. In this case, it's a chi-square statistic, just to get an idea of how good these features are going to be. But really, the important thing for you is the left field of each row, which are my features. And again, we're not doing this problem now. I'm just going to give you some example of notions of representations. Yes?
So 2 questions. The first is this a list of things that you thought out to look for, or were they generated by the data when you gave these constraints?
Okay. So I had to dream up the feature types. The rest is automatic. So once I define the feature types, I can write a program that instantiates them in the data. Okay, is that answering your question?
Yeah.
Now, but I did have to dream up the feature type. Just like a few minutes ago, you had to dream up a representation for sentences. You suggested a bag of word representation, which is okay. I suggested a slightly different representation, somewhat more expressive. We have to do this, one way or another. You can either say it's just a bag of words. That's a decision that you as the modeler needs to do. I suggested a slightly different modeling. I think it's going to work better. But either way, whether it's a complex modeling or a simple modeling, you have to do this. Okay, so what happens next? Once I decided on the types, I have to go to my text and do this automatic step of, here are the types, let's instantiate them. So I'm going to the sentences, I put brackets around each target word. I only took sentences from Wikipedia that have either weather type 1 or weather type 2, and I designated them using these brackets that you can see, but whether the murder of E1 benefactor, that's the top sentence there, I'm looking at 2 words before and 2 words after. In this case, I don't have 2 words before, because it's the second word in the sentence. And I'm instantiating my type 1, 2, 3, 4 features. So for example, I can say -1W, but is a feature in the first sentence. +1 W, the is a feature. And so on. Okay. And then I name the features. I don't want to carry strings like this. I can name them. You can carry strings if you prefer. What I did is I named them, and basically each example now is a list of features. Where the first, in my encoding here, the first number is the label. You'll see that all the first numbers are either 1 or 0. 1 is weather type 1. 0 is the other type of weather. And then indices of the features. One interesting thing that you see here is that I have variable numbers of features. Why? Yes?
Some examples are to express some features and not others.
But why is that happening? Why, when I sit on a sentence and I extract the features, I can get a different number of features than if I sit on another sentence? The sentences are different, but why is the number of features different? Suggestion?
Whether can occur more than once in a sentence.
That's one option. other options that are even more likely, yes? If the sentence starts with weather, or if the first word is weather, I don't get the -2 or the -1. If it's the last or next to last, I'm missing something. If I have repeated words in my small window, I only count their presence, not how many times they appear. All these things accumulate. That's one reason. Now, here you see very extreme differences. Why is that? It's actually because what I'm showing you here is the test data, not the training data. Why is that? Why does it make a difference? We are getting to deep questions here. You will have to go back to these questions when you start doing homework. Maybe it will come up in homework too, but this is a really important question to think about. So why is it in the training data you will see differences due to everything we just said? First word, last word, and so on. In the test data you will see even more differences. Why? Yes? That's a possibility, but no, I'm only going to put there things that have one of the weathers. So something else. Yes? That's true, but why does it happen that I have such variability in the size of the examples, in the number of, basically what is the size here? It's the number of active features in a sentence. So let's think about it. What is my training data doing? My training data defines the feature space. All right, so I gave you 4 types, and then you go through each sentence in the training data, and you translate it into a set of features. You define your lexicon, if you want, the set of words that you've seen, and as a function of that, the set of features that you have. Now comes a test sentence. What could happen in the test sentence? Yes?
You can encounter something you didn't see.
Yeah, I can see words that I've never seen in training. So I don't have a feature number for them. They're not in my lexicon. So if I see in my test data, following the word weather, the word chair, and I've never seen chair in a ±2 window in my training data, I don't have a feature for it. I can invent a feature, but it doesn't matter. I didn't learn using this feature, so it doesn't have a weight, it doesn't count. So in my training data, I define the lexicon. That's what I know. That's the only thing I know. It doesn't matter what sentences you give me. I know what I've seen in training. Now you give me a new sentence, it could be even that my representation for it is going to be empty. Look at the third line there. It only had, oh, it's not a good example. Actually, this is a continuation. Anyhow, I can show you examples that are almost empty, because this was a sentence that used vocabulary that I've never seen in my training. It's going to be difficult to do something with it. The feature representation for it is going to be very, very sparse. Okay? So again, this is something to remember when you start playing with algorithms, that sometimes it doesn't matter what you've done in training, you see a new test example, you have no idea what to do because you haven't seen anything similar. In our case, the only thing we know are the features. That's it. You can throw away this text once you encoded it this way. That's what you know. And if the test data does not use the same lexicon, nothing you can do. Okay. So now we're getting, so we talked about modeling, we talked about representation. We're going to just start talking about the third step in my 3-step slide: modeling, representation, and learning. How to learn. So now my goal is, I already know how to represent the blue point and the red point. We already agreed that we're going to look for a linear function, so a weight vector, W. And we know once we have the weight vector, how we're going to make decisions, right? So we're going to do the dot product Wx. If it's positive, we're going to say red points. If it's negative, we're going to say blue point. Now the question is, how do we get this W? So how do we get this W? How do we learn this linear function? Yes?
Start with a random line and measure the log.
Okay, good suggestion. So let's start somewhere. Start with a random W and see how well we're doing and correct it. What does it mean, how well we're doing? Here. So if everyone buys into this methodology, essentially it's going to be an iterative algorithm. That's the suggestion. We have to figure out how to correct. And we have to figure out based on what to correct, what's going to drive our correction, right? So these are really the two decisions that we're going to make. So we're going to start with a linear threshold function, see how well we're doing, correct, repeat. Very simple algorithm. We still have to make a few decisions, right? So first of all, let me make a comment that there are other ways. I mean, not all learning algorithms are necessarily going to be iterative. Not all linear learning algorithms are necessarily going to be iterative. There are going to be algorithms where we're going to look at the data, compute something, boom, we have the model, without iterating through the data, correcting, fixing, and so on. But now, we're going to do it this way. And the first step is see how well you're doing. So what does it mean to see how well we're doing? And already here, we see that we basically answer one of the most fundamental questions that we have in learning. The goal is to predict an unobserved output value y based on an observed input vector x. Or, saying another way, I want to understand this functional relation, f of x from a set of pairs xy. We are actually talking now only about classification. So we're mapping, y is going to be a discrete number. But what do we want it to satisfy? I mean, how do we decide how well we're doing? What we want is we want to minimize what we're going to call a risk or a loss, L of f. What is this really? It's essentially the expected number of mistakes we're making. The expectation over the space x cross y, capital X cross capital Y, of f of x is different than y. That's what we care about, right? Essentially the expected number of mistakes. Now, this is going to be called a loss function. We're going to use this term a lot today and next time and throughout the class. In this case, think about what's in the brackets as an indicator function, right? So it's either 1 or 0. Either f of x is not equal to y, or f of x is equal to y. And I'm taking expectation over this. In a simpler term, I'm counting how many mistakes I've made over my data. Now, it's important to notice that while I want to minimize this, I cannot. Because to minimize this, I need to know the distribution of the data. Now, if I know the distribution of the data, there's no learning problem, right? I can just do argmax over y of p of y given x, compute it, we're done. The reason we have learning is because we don't have the distribution over x cross y. So let's ditch that and continue. So I want to minimize this loss, but I cannot. So what I'm going to do is I'm going to minimize the empirical loss. You give me training data, I'm going to try to do my best on the training data. That's what we call the empirical loss. So basically, now I'm moving to L, to what I denote here as L prime. It's essentially 1 over m, m is the size of my training data, of the number of times f of x is different than y. Okay? Now, of course, you can ask, why is that relevant? I mean, you're just minimizing on the training data. Who cares about the training data? You care about the test data that you've never seen. And that would be a legitimate question that we want to try to address, and we will address as we go ahead. So the intuition is going to be that if m is large enough and you're doing okay on this m training data, and the distribution that you see in training is about the same as the distribution you'll ever see in the world, doing well on this sample is going to guarantee that you're going to do okay also in the future. That's the intuition. We're going to make this more rigorous in a few weeks. But for now, that's what we are doing. So there's another problem with this. This is typically difficult computationally. So even in the linear case, what does that mean to minimize this? It means that, look at these blue points and red points, or purple and red points. The problem of find the line, the separating line, that minimizes the number of red points that move to the other side, plus the number of purple points that move to the other side, that problem is NP-hard. Some of you know what that is, some of you may not. It's a computationally hard problem. If n is large, you just cannot compute. And therefore, what we're going to do is we're not going to try to do this. We're going to try to approximate it. So rather than work on the loss function that we care about, we're going to try to work on a surrogate loss that will be an approximation that we believe makes sense. And that's another assumption that we're going to make. Learning is going to be driven by loss functions that we believe make sense, and they're going to drive our learning algorithm. For example, rather than this loss function, which is the one I cared about here, I could suggest another loss function, which is called squared loss. F of x minus y squared. Now think about it. If the real loss function that you care about, which we're going to call 0, 1 loss, the misclassification error, if it's 0, I made no mistakes, then this new function is also 0. Right? You can see that. However, it can be that this one is small, and my misclassification isn't that small. They don't completely correlate. Nevertheless, it's a simple loss function to minimize, and I'm going to do this. We'll see it next time and over the next few weeks, many other loss functions that we're going to use to drive our learning. The important lesson for today, which is the last minute, is that loss function is important, and it's a bit of an art to decide which loss function you're going to use to drive your learning. So, in fact, I'm going to stop here. We're going to continue with loss functions and with how to develop algorithm as a function of it on Monday. Okay, have a good weekend. Yes? What? They don't completely correlate. So you can actually show that you drive it with this, and you still don't minimize the mistakes. Oh, you're welcome. Okay. Sure.
we don't have we cannot select the course anymore. So can I get into this class anymore?
Yeah, so I talked about, were you here at the beginning of the class?
Yeah. It's like a petition.
There is a petition. Yeah.
What is the petition?
So you have to complete a form that you want to change your, you want to register to the class even though the deadline is passed. I need to sign it, and I think someone in your department has to sign it. So if you want to, now at this time you can still not petition because the class is completely full, but next week I think you'll be able to do it. So if you want to get details, in my Piazza note I mentioned the name Nicolas, I can't remember his last name, but I mentioned it in the Piazza. Send him email and ask what do I need to do in order to petition. He will give you a form.
Okay, and even though I do the petition, there is no guarantee that I can get into class, right?
There is no guarantee. In fact, the college could reject your petition, but we talked to them and told them about the situation with the waiting list, and they promised that they will accept our petition. So that's the only thing I can say.
Okay, thank you so much.
So what about the PPTs? Will they be uploaded in Piazza and the assignment? I'm also in the waiting list still now.
Yeah, all the assignments are on the website.
Okay.
Everything is on the website. The quizzes, the assignments, you don't need Canvas to do it.
Okay. So the PPTs?
The PPTs are already on the website.
Okay, fine.
Yeah.
So mostly you'll be expecting a petition next week, as you said.
I hope that next week will be, yeah. My assumption is that next week we'll already have some slots. For sure, after W1, homework 1 is made available, people will drop the class. So I know for sure, I've done it a few times, and I know that people will drop it, so there will be slots. Hi.
Just wanted to say thank you for letting me in your side. So I'm auditing you guys.
Oh, okay.
Yes, that's it.
So that works. Okay, sounds good.
And I saw I was added to Canvas also, which is cool. After I was like ready.
You asked the TA to do this?
No, I thought I was just automatically added to Canvas.
Okay, I don't know how this happened. But it's good.
Yeah, but I've just been like checking, like since everything's on the website.
Yeah, everything is going to be open on the website, so you actually don't even need Canvas.
Okay. But yeah, so I know I'm still submit. So I know homework sure wasn't.
We're not going to grade.
Okay,
No, we're not going to grade.
So
So,
I should
because
just not submit like this.
no, but look at it,
Yeah.
and we're going to give solutions for everything.
Okay, yeah, that's what I was
Yeah.
wondering, because I want to.
Yeah, so the solution will be available on the website after the deadlines, 4 days after the deadlines, because we give some slack.
Maybe this is like more like a question for.
Yeah, it probably is because I actually have to run.
Okay.
I have a train to catch. So come to my office next week, and I'll be happy to answer questions. You're welcome. What's your name? How do you spell it?
IYU, or most people just call me Z.
Okay, and your last name?
Last name is here,
Yeah.
Y.
Okay, thanks.